Hello, everyone. In this video, we're going to look at inferential statistics. In particular, we're going to look at a method called hypothesis testing in inferential statistics. But first, let's get into the definition. So the definition, inferential statistics is the process of drawing conclusions about a population parameter based on a sample taken from the population. So just some examples of some population parameters that we try to draw conclusions about or predict include things like the population proportion, P, the population mean, mu. We often look at a difference between two different population means. So that looks like the difference of two means or two proportions. So P1 minus P2, or say mu1 minus mu2. So here's some examples of those parameters. And just to review some notation, we call the corresponding sample statistics. For a proportion, we call that p hat. For a mean, we call it x bar. So again, just notation, population parameters. We have some notation here, proportion, mean, differences of those. And we also have our notation for sample statistics, p hat, x bar, which are the sample proportion or sample mean. So now let's just recall some examples of populations and samples. So one example of a population is all of Washington state residents. All WA state residents. Now, it would pretty much almost be impossible to collect data on everyone in that population. So in order to find information about that population, we might collect a sample of, say, 100 or 1,000 randomly selected people. So maybe we'll highlight some of them here. We want to take a good representation of everyone in the state. All right, other examples we might have. So suppose maybe we are growing some Washington apples, and we have all of the apples in our orchard. So here's our box of apples. Make this authentic. We'll have red apples in there. So here, the population. It's all of the apples in our orchard. And now we might want to collect data on these apples, say their sweetness, how long they last on the shelf, but we don't want to collect, and we can't collect data on every single apple. So we might take a sample that includes maybe a bucket of our apples where we've sampled our apples from across our orchard. All right, so now let's get into some of the details of inferential statistics. So there are three main assumptions and considerations in the topic of inferential statistics. So first of all, when we're doing this work, we want to assume that the sample is likely a good representation of the population. So that means we need to collect an unbiased sample. An unbiased sample collection. So for example, if we're sampling all of the people in Washington state, we wouldn't just want to sample people in Seattle or just people in Olympia. We need to collect data on everyone throughout the state. Number two, there's an element of uncertainty as to how well the sample represents the population. So because we're collecting data on just a subset of the population here, we are going to get differences in the sample statistics that we calculate. from different samples. So I'll write that note here. So each sample will have slightly different sample statistic. And that, again, is because each sample has a different collection of people or apples that we're collecting data on. So the statistics that we get, the proportion or the mean for each sample is going to look a little different. So we see there's some variation when we're collecting data on a sample. And so in our inferential statistics, we need to be mindful of that variation. So we'll see here in a little bit that there is some probability coming into play. All right, but number 3, our third consideration, the type of parameter we are predicting influences the methods we use for making an inference. So we saw some examples of the types of parameters we might use. So, or we might want to draw conclusions on. So proportions, means, etc. So based on which type of parameter we're using, we're going to use a slightly different method. And maybe rather than method, we'll say calculations. So the method that we're going to see here in a bit, hypothesis testing, we can use for all of these different parameters, but the calculations involved are going to be slightly different. Use a different formulas or calculations. Don't worry, in this video, we're not going to get into the details of each of these different types of formulas, but I will refer you to where you can find information about calculating the values necessary in the hypothesis test for each type of parameter that you might be interested in. All right, so now let's get into hypothesis testing. So a main method for determining information about a population, so this whole business of inferential statistics, is to use a hypothesis test. For such a test, we make an assumption about the population and then collect data to see if our prediction is correct. So that's the main story about hypothesis tests. We create a hypothesis, a prediction, then we go out and collect data and see, is our prediction correct? So here are the main steps involved in a hypothesis test, and we'll go through them in a little bit in more detail. But first, just to summarize. So the first step is to create a hypothesis. We then determine a significance level, and we'll see what that is here in a moment. We then collect sample data. From that sample, we calculate what's called a p-value. With that p-value and significance, we decide an outcome of our test. All right, so let's get into these steps in detail. So first, creating a hypothesis. So a hypothesis, and in particular, is a hypothesis about our population. And in fact, I've double stated it here. I even stated it in the notes. So this is our guess or assumption about the population parameter. So we use notation for these hypotheses. So H sub 0 often or is called the null hypothesis. This H sub 0 is often called H naught. So I'll write that out here so you have it in your notes. So we say H naught, like that. Like there's a little naught, a little 0 down there. And this null hypothesis, this is the status quo, meaning this is kind of what, if nothing out of the ordinary were to happen, this is what we think is true about the population. So for example, maybe we're flipping a coin and we want to test, is this coin fair? Well, our null hypothesis would be, yes, the coin is fair. So we might collect data on the proportion of heads that come up for this coin. So that null hypothesis would look like P. We could say proportion of heads should be equal to 0.5. 50% of the time, we should get a head. So this is just an example. So then the alternative hypothesis is often called H sub A, H sub little a. This is the opposite of the null hypothesis. So in our coin example, H sub A would be P is not 0.5. Or we might get more specific, say we think that the coin is favoring heads. So we might say that we think the proportion is greater than 0.5. Based on the structure of our alternative hypothesis, we are going to use a slightly different formula in some of the calculations below. So when you're doing some of your own research or when you're calculating these tests on your own, you need to consider what kind of alternative hypothesis you're using. If we have just an inequality like this is called a one-tail test. If we're using a not equals to, this is called a two-tail. We're not going to get into too much of that detail in this video, but this is just some language in case you look up some of this information on your own when you're doing your own research. All right, so we set up a hypothesis where we have our null hypothesis and alternative. Now we need to determine a significance level. Well, what is a significance level? The significance level is the probability that the null hypothesis is wrong when really it is correct. This is often called a type 1 error, and you'll see more about that in the error video and section as well. So typical values of the significance level is 0.05 or 5%. And we have notation for the significance level. We call it alpha, and we write that symbol like this. Greek letter A, alpha. And we'll see where this significant level comes into play in a hypothesis test when we look at step 4. All right, so now in step 3, we need to collect a sample. So we take a sample of the population, keeping in mind that we want the sample to be unbiased and do a good job at representing the population. So we take a sample of this population and collect data on it. Then we compute the sample statistic from the sample. So that could be the sample proportion, that could be the sample mean, that could be the difference of two sample proportions, difference of two means, etc. Okay, so far we have our hypotheses. We have a significance level, alpha, and we have a sample stat. Now with that information, we calculate a p-value. So what is a p-value? A p-value is the probability that if, really important, if the null hypothesis were true, then sampling variation, that differences of sample statistic, just that happens naturally from sample to sample, would produce an estimate that is even further away from the hypothesized value than our data estimate. All right, let's break this down a little bit with a picture. So if the null hypothesis were true, let's assume that we're working with a population mean. So if the null hypothesis were true, then the population data, or better yet, the distribution of sample data, would look something like this, where the center is above that true population mean. So I'm going to write out this distribution. This is a distribution of sample data if H0 were true. So we can actually draw these distributions starting with a hypothesized population mean. And how we do that is through simulation. So we assume that a population has a mean of mu then we can do computer simulations and they will collect samples of this population. Here's our population. The computer will collect various samples of that population and then plot on this distribution the sample statistic. And so we get this nice curve like this. Okay, so this is if the null hypothesis were true. So then what we do is we go and collect our data. So we find the sample mean of our data. And we place that sample mean where it falls on this distribution. So maybe X bar lives here. So this is where X bar is. So then the p-value is going to be this area under the distribution. And we see that we can interpret this area as a probability. I'm going to write that over here to the left so we have room. So this p-value is the probability that the sample data is either at or further from that mu, that center, than our X bar. So this probability here, or this area here, is the p-value. And then so we can also visualize where we see alpha on such a distribution. So alpha, that significance level, gives us a level for what type of probability we're willing to accept in our p-value. So suppose alpha is here. We want to accept that we're only this amount of the time likely to make one of those type 1 errors. So this would mean that p-value falls outside or within the alpha. So we're going to say this must not be true. We're only willing to accept whenever our p-value is going to be larger than that alpha. We'll break that down in a minute, but I just want to show you the visual there of comparing alpha and the p-value, which will get it into step 5. But before we do that, let's just finish off this step. So how do we compute those p-values? So I mentioned that we can do this simulation on a computer where we create this distribution. So that's one way. And there are various computer programs that can do this. Some of them include GeoGebra. Desmos also has a feature that can do this. There's also StatCrunch. So that's one way. We can also use computer calculators. So Excel, GeoGebra, as I mentioned, Google Sheets, they all have calculations and formulas for computing p-values. We will link to some other videos if you're interested in learning more about those computations. All right, so after collecting that sample statistic, finding the p-value for that sample stat, now it's time to decide the outcome of our test. So how do we decide that outcome? But we compare that p-value with the significance level alpha. And what happens? Well, if p, that probability that sample data is at or further away from our sample, if that's smaller than alpha, then we choose to reject the null hypothesis. So meaning we say that this must not have been true, this distribution, because it's so unlikely for that X bar to happen if this were true. And so we say that the sample gives you evidence that the null hypothesis is wrong. So we say, nope, this must not be right. But what happens in the other situation? So what if p is actually larger than alpha? So meaning it's fairly likely for us to find that sample statistic that we did. Then what we say is we fail to reject the null hypothesis, and we have no conclusion on this test. So notice our two decisions are not fail to reject the null hypothesis, or are not rather reject the null hypothesis. and accept the null hypothesis. We can only fail to reject. And why is that? Well, this test doesn't prove H0 is true. I'm going to write that note. Does not prove H0 is true. Because our sample statistic and the null hypothesis value, H0, they might have just been off both together. Might have been off, meaning not true, together. So we have no conclusion. No, we can't make a conclusion about the population in this second case. Okay, so let's just put this into context and look at a few examples of doing hypothesis testing. So in these examples, we are going to determine for each scenario, we're going to decide whether to reject the null hypothesis or fail to reject the null hypothesis based on the stated p-value. And we're going to include an appropriate conclusion. So here we're not actually going to go through and compute p-values. We're going to be given them. But this will help us to make a little bit more sense of the steps in a hypothesis test. It'll help us set up the hypotheses, compare the p-value with the significance level, and then make sense of the conclusion. All right, so let's jump in. So part A says, a company is concerned that too few of its cars meet pollution emission standards. They have 1,500 cars. So that's their total population. They sample 56 cars and find that 43 meet the emission standard. So we can make some highlights here. So we're interested in meeting the emission standard. And we have our sample that 43 out of 56 do that. So now this company wants to test if less than 80% of their fleet meets the emission standard. They run a hypothesis test and find that the p-value for this sample is 0.0009. All right, so let's go through the steps. So first of all, we need to set up the hypotheses. So H0 and HA, or H naught and our alternative. So what are we assuming here about our population? Well, we want to test to see if less than, and we'll highlight that here, less than 80% of their fleet meet the emission standard. So the status quo then would be that 80% of their fleet does reach that standard. So P equals 0.8. And just so we're really clear here, P is equal to the proportion of all cars, or at least all the 1,500 that they have, meeting standard. All right, so then the alternative here is that less than 80% meet that standard. Right, now what other information are we given? Well, we're given that the p hat is equal to 43 over 56. So we can even compute that proportion. Oh, and I hope you caught me here. I miswrote. We have 43 that meet the emission, not 45. So we have 43. So we get about, we'll approximate here because we have a lot of decimal points, 0.767. We'll round up to 8. So this proportion of the sample is less than that 80%. So now using a hypothesis test where we compute the p-value, we can determine, is this significant? Is this smaller proportion significantly less than 0.8? That's essentially what the hypothesis test is going to answer for us. All right, so let's continue that test. So we've taken this sample data. So from that sample data, we have computed a p-value. Well, they've done it for us. They found that p-value to be 0.0009. In other words, as a percentage, that would be, move that decimal place over twice, 0.09%. So that's the probability that we would get this sample proportion if, indeed, 80% of the cars met emission standards. So that's a very small probability. So it's very unlikely that we would get this sample proportion if this was true, if the population actually had 80% of its cars reaching emission. And so if we can decide that we want to use alpha equal to 5% here. So let's use alpha equal to 0.05, in other words, 5%. So we can compare our p-value with alpha. So how does 0.0009 compare with 0.05? We see it's for sure smaller. That p-value is smaller than alpha. So the p-value is small, so small, it's smaller than alpha. So what do? We reject 80, and we can even say there's evidence for the alternative. All right, but let's make sense of this conclusion in the context of our problem. So we can summarize. So we are going to reject 80. And why is that? Well, with a p-value of 0.0009, we can say there is evidence in favor of that alternative, meaning that less than 80% of their cars, we call it a fleet, of their fleet meets emissions standards. All right, so there's our conclusion. And just to bring it home, we rejected our H0 in favor of evidence for our alternative. All right, let's look at the next two scenarios. So now looking at part B, we're told that in 2014, the official poverty rate was 14.8% in the US. A city official wants to test if their country has a different poverty rate than the rest of the US. I'm assuming this is their county or city, so let's assume it says city, has a different poverty rate than the rest of the US. He runs a hypothesis test and determines the p-value to be given as 0.273. So let's first just determine what is the parameter that we're measuring. So we're considering the poverty rate. So let's let P equal the proportion of poverty. And we're looking at this certain city. So proportion of poverty in the city. And we want to determine what? We want to determine if our city has a different poverty rate than the rest of the US. So status quo would say that our poverty rate was equal to that of the US, so equals 14.148. So then we want to test if actually our proportion of poverty is not equal to that 14.8%. So here would be the setup of our hypotheses. So now what information are we given? Well, we're given the p-value. So we're not given the sample statistic here, but that's okay because we already have the p-value, which we use the sample statistic to compute that p-value. But when given a p-value, we can just use it straight up. So the p-value we're given is equal to 0.273. So what that means is it's 27.3% likely. So 27.3% of our samples that we take should have the proportion similar to the proportion that we collected data on. So now, how does this compare to that significance level of 0.05? Well, we see that this p-value is larger than that significance level. So the p-value is not very small. It's pretty likely that we're going to get the sample statistics that we got in this situation. So what that means is we fail to reject H0. So just going back, so we're in this second situation here. The p-value is larger than alpha, so we fail to reject the null hypothesis. So let's go ahead and write that out. So here, the p-value is not too small. So what does that mean? We fail to reject H0. So we can't say that our city is not at a 14.8% poverty rate. So fail to reject that H0. We can also say there's not enough evidence for the alternative for HA. Okay, so let's put this in a little context. So we'd say we failed to reject H0 because with a p-value of 0.273, there is not enough evidence that their city has a different poverty rate than the rest of the US. All right, nice work on that. So let's just finish off by looking at this last part here. So we can even go a little faster now that we're getting used to working with these types of objects and words. So let's go ahead and read the situation. So drugs that prevent seizures sometimes have unwanted side effects, such as depression. A researcher wants to study such a drug and look for evidence that such side effects exist. So she runs a hypothesis test and finds her p-value to be 0.06. So here we're not given a specific parameter value. We're just wanting to know, a researcher wants to study such a drug and look for evidence that there are side effects. So then the status quo would be no side effects. She wants to show evidence that there is. So the alternative would be yes, side effects. All right, so what's our p-value here? So here, maybe, so as is, we haven't written a population parameter, like a numerical value, but we get a sense of what we're looking for. So maybe what this would look like in context is that she'd measure the proportion of people in her sample that, say, had side effects. So the percentage that had side effects. And then she'd want to determine what that number was that was acceptable. So maybe if P was this proportion, this percentage was greater than 20%, she'd say that's going to be evidence that there's side effects. So then we'd want to test P being equal to 20% or P being greater than 20%. Okay. So that's just a little background of where we might see this with numerical context. Okay, but this is essentially what she wants to test. So we have a p-value of 0.06. And then we'd say, well, how does this compare to the alpha of 0.05? So the p-value is pretty small. 6% of the time she'd get the data that she found in her sample. But this 6% is still an acceptable probability for us because it's larger than alpha. So here we'd say p-value is not small enough. So what do? So we fail to reject 8.0. And we'd say there's not enough evidence for the alternative hypothesis. All right, so let's put that in context, our conclusion. So we fail to reject 8.0 with a p-value of 0.06. There is not enough evidence to conclude that such side effects exist. So we fail to reject this. So we fail to reject that there are no side effects. And we can't conclude that there then are side effects. All right, awesome work going through these notes. Again, we'll link to some other videos that will go into a deeper dive of looking at and calculating these p-values. That's really the only component here that we didn't look at in this section. But this video and these notes should give you a good sense of what it means to do a hypothesis test to make inferences about a population, which again is a main method that we use in inferential statistics. Thanks for watching.